The cosmos is stranger than we ever thought. For a long time, looking for life meant looking for another Earth. Find a planet like ours, and maybe you find life. That whole idea is gone now. It's been torn apart, and what we've found since these new worlds, they've made us start over. There are 30 of them. Each one shows a different possibility. A different way life could exist. A diamond world. A planet that's just an endless ocean. Worlds that don't even orbit a star, just drifting out there. So the old rule is gone. What if life doesn't need water? What if it needs something else, something exotic? Could a planet with 2 suns support life? Or a world with no sun at all, could it? These places force the question, and by the end, the idea of a habitable world, it changes. It completely transforms. So what does home mean then? If it could be almost anywhere, the idea was simple, it made sense, it came from the only life we knew. We called it the Goldilocks zone. Around a star, there had to be a space that was just right. Not too close where water boils, not too far where it freezes, but in the middle where a planet could have liquid water. For a long time, that's where we looked. Find a planet in the zone and you had something, miss it and you moved on. It was logical. For a long time, it was the whole plan. But the universe had other plans. The first crack came from a place of destruction. Astronomers found planets, but not around a sun-like star, around a pulsar. A pulsar is the dense, spinning corpse of a giant star that exploded. It sends out beams of intense radiation, like a deadly lighthouse. That a world could exist there was shocking. But to find one there meant the rule was wrong. If a planet could survive an explosion, bathed not in sunlight but in deadly rays, then what did habitable mean? It forced a question. Is liquid water the universal key to life? Or is it just the key that worked here on our planet? What if, in all the possibilities, life could use something else? A different liquid like methane or ammonia flowing under an alien sky. Or what if it didn't need a solvent at all? The pulsar planets whispered that the ingredients for life might be more flexible. They hinted that energy could come from many sources: tidal forces, radioactive decay, the fierce glow of a stellar remnant. The search wasn't about finding a new Earth anymore. It was about learning to read a much stranger cosmic alphabet. 1995. The first shock came from 2 astronomers, Mitchell Mayer and Didier Queloz. They were looking at a star, 51 Pegasi, not looking for a planet, but the data came back. It showed something that shouldn't be there, a world half the size of Jupiter. But it wasn't far out where it was supposed to be. It was incredibly close to its star, an orbit of just 4 days, a hot Jupiter. That discovery broke the model. The quiet order of our solar system. Every theory said giant planets form slowly, far out where it's cold, where ice and gas can collect. This world, 51 Pegasi b, was in a furnace. Its existence meant one thing, a terrifying thing: planets move. A giant planet can form in the cool outskirts, and then, through gravity, it can spiral inward. It migrates. That changes everything. You have a new solar system forming, peaceful. Earth-like worlds might be taking shape in the temperate zone, and then a Jupiter-sized planet begins to move inward. Its gravity is a wrecking ball. It scatters the smaller worlds, flings some into the void, hurls others into the star. It reshapes everything, the whole architecture. This one world taught us a planet's current address isn't its birthplace. Our own solar system, with its orderly orbits, its stable zones, might be the exception. Not the rule. For habitability, that's a brutal new filter. A planet needs time. Eons of stable conditions for life to emerge, to evolve. If planetary systems are often scenes of chaotic migration, of gravitational violence, then that kind of peace, that long-term stability, becomes rare. A precious cosmic rarity, the dance of the planets isn't always a graceful waltz. Sometimes it's a collision. The silence around pulsar PSR B1257+12 is complete. It's the silence of a graveyard. This stellar corpse spins 700 times a second, sweeping the cosmos with a radiation beam so intense it would strip a world bare. But in 1992, astronomers found planets there, 3 small worlds orbiting this beacon of death. They were the first exoplanets ever confirmed. They shattered the quiet expectations of where a world could call home. This was a solar system born from an apocalypse. The pulsar is all that's left of a massive star that died in a supernova, an explosion so violent it should have vaporized any planets that were there. So their existence meant they were survivors. They either endured that unimaginable blast or they formed from the ashes afterward, a second generation born from the wreckage. For habitability, this was a profound leap. It tore the rulebook in two. If planets could persist in an environment bathed not in sunlight, but in lethal particle beams and X-rays, then our definition of a possible home was far too narrow. Life there would face impossible challenges. The surface would be scoured, but the discovery forced a new question. What if life didn't need a sun? What if it could draw energy from somewhere else? The pulsar itself provides a brutal, constant torrent of energy, and tidal forces, as these worlds are stretched and squeezed by the pulsar's gravity, could heat their interiors to the point of creating subsurface oceans, molten rock or water sealed away under a protective crust. This introduced a critical idea to the search. Alternative energy sources. A planet doesn't need a gentle yellow star. It needs energy, and energy can come from many places. The gravitational dance of moons and planets. The radioactive decay of elements in a world's core. Even the relentless glare of a stellar remnant. The pulsar planets taught us that planetary systems aren't always born into peaceful orbits. They can be forged in fire and survive. They hinted at a cosmic tenacity, a resilience we hadn't considered. If worlds could exist there, in that most hostile of places, then perhaps we should look more carefully at the quieter, dimmer stars next. The failed stars, brown dwarfs, or the lonely rogue planets drifting between the stars. The criteria for habitability had just lost its dependence on a sun like our own. The universe, it seemed, was full of darker possibilities, stranger ones. That pulsar was a silent, spinning beacon. It taught us to look for energy in the darkest places. But the next discovery made us look at light differently. It came from a world that was disappearing. Astronomers pointed Hubble at a star 150 light-years away. At a planet called HD 209,458b, another hot Jupiter. Its year was just 3.5 days long, but this time they didn't just detect the planet. They saw its atmosphere. As it passed in front of its star, Hubble caught the starlight filtering through the outer layers of this gas giant. For the first time, we weren't just seeing a dot of light or a wobble. We were analyzing the chemical makeup of an alien sky. They found sodium. They found evidence of a vast, puffed-up envelope of hydrogen gas. And they realized something. This planet was evaporating. The intense heat from its star was boiling the atmosphere away, stripping it off into space, creating a giant, comet-like tail of lost gas. They named it Osiris, after the Egyptian god of the afterlife, a being torn apart and then reborn, a fitting name for a planet in a state of cosmic dissolution. For the search for life, this was a revelation with two sides. First, it opened the door to atmospheric characterization. If we could detect sodium in the sky of a gas giant that far away, then one day we could look at smaller, rocky worlds. We could search their atmospheres for the chemical signatures of life, for biosignatures, a strange abundance of oxygen which on Earth is made by plants, or methane from microbes. The dream of sniffing the air of another world became a real possibility, but Osiris also delivered a warning. It introduced the concept of atmospheric escape. A planet can lose its life-sustaining envelope. If a world orbits too close to its star, the constant barrage of radiation and particles can, over time, strip the atmosphere away entirely. This isn't just a problem for gas giants. A rocky planet like Mars is thought to have once had a thick atmosphere and flowing water, but it lost its global magnetic field. Without that protective shield, the solar wind slowly scoured its air away, leaving the cold, thin atmosphere we see today. So Osiris taught us that habitability isn't just about being in the right place. It's about having the right defenses. A strong planetary magnetic field acts as an invisible shield. It deflects the stellar wind. It protects a world's precious atmosphere. A planet might be in the perfect Goldilocks zone, but if it lacks that magnetic armor, its chances for life could evaporate, just like the tail of gas streaming from Osiris. The criteria now had to include planetary geology and magnetism. A living world needs a heart that is still beating, a molten core that spins and generates a protective field. It needs to be able to hold onto its sky. Osiris showed a world that lost its sky. Then came a world that might have kept one, a world that could be like ours. In 2010, astronomers announced something big. They'd found a planet around a small, dim star, a red dwarf called Gliese 581. They named the planet Gliese 581g. And they said it was different. It was small, probably rocky, and it orbited right in the star's habitable zone. The headlines wrote themselves, Earth's twin. The first habitable exoplanet, but then the story broke apart. Other scientists looked at the same data. They saw the wobbles in the star's light, and they couldn't find the planet. They said the signal wasn't strong enough. It might just be noise, a ghost in the data. Gliese 581g became this fierce debate. Was it a real world or just an artifact? This controversy did more than question one planet. It reshaped the whole search. It forced a realization. Just being in the habitable zone wasn't enough anymore. We had to prove what a planet was made of. The zone around a dim red dwarf is much closer in. A planet there would be tidally locked. One side always day, the other always night. Could an atmosphere move heat around? Could a magnetic field hold against the star's flares? Gliese 581g, real or not, made these questions urgent. It pushed astronomers to build new tools, to measure not just a planet's orbit, but its mass and density. A low density means a gassy world, like Neptune. A high density means rock and metal, like Earth. The idea of habitability changed. It went from a single line on a chart to a checklist. Location was the first box. Composition was the second. Atmosphere the third. Magnetism the fourth. Each one a hurdle a world has to clear. A potentially habitable planet became a statement of probability. Not certainty, it was a world that passed some tests with others still pending. This shift in thinking set us up for something stranger. What if a planet passed the location test and the composition test, but was made of something completely alien? Not rock, but something else. The next discovery would be a world not of continents, but of a single, endless ocean. A water world. The debate about Gliese 581g left this question. We could talk about signals and habitable zones, but what were these planets actually made of? Kepler gave us the answer. It launched in 2009. It was just this telescope staring at one patch of sky. Its job was to watch for the tiny dips in starlight, a planet passing in front. That method, the transit, it was precise. It told you a planet's size, but then in 2011, Kepler found something. It found Kepler-10b. The data was clear, a planet 1.4 times the size of Earth. The breakthrough came from combining that with other data. They calculated its mass. From the size and the mass, you get density. The numbers were undeniable. Kepler-10b was dense, incredibly dense, rock and iron. It was the first unquestionably rocky exoplanet, a scorched ball of lava orbiting in less than an Earth day. Surface temperature hotter than a blast furnace, over 2,500 degrees. For the search, this was a landmark in two parts. First, it was a validation. It proved planets built like ours, terrestrial worlds of stone and metal, weren't rare accidents, they were common. The galaxy was full of them. The building blocks for Earth-like worlds were everywhere. But Kepler-10b also delivered a brutal lesson. It showed that being the right size, the right composition, meant nothing if you were in the wrong place. This was a terrestrial planet in every sense, but it was a hellscape. Its existence drew a bright line. It separated the idea of a rocky planet from the idea of a habitable one. Orbital distance and temperature weren't secondary details. They were the primary filters. A world could pass the composition test and still fail the most basic requirement for life. A temperate environment. This forced a sharper focus. If we wanted to find a living world, we couldn't just hunt for rocky planets. We had to hunt for rocky planets in temperate orbits. Kepler-10b was a signpost. It pointed away from the infernos toward the more gentle, distant orbits. It told us where to look next, not at what was easy to find, but at what was truly possible. And what was possible, as the next discovery would show, could be a world utterly drenched, a planet with no land at all. Kepler-10b was stone and fire. A place where any hope for life just burned away. But then the next year, Kepler showed something else entirely. In 2011, they announced Kepler-22b. This was the first world they'd found, orbiting right in the habitable zone of a sun-like star. Not a red dwarf, a star like ours. The planet was about 2.4 times the size of Earth. It had a gentle orbit every 290 days. The data suggested a world bathed in starlight similar to ours. With an Earth-like atmosphere, its surface could be about 72 degrees. The news was electric. Here was a planet in the right place. The psychological impact was deep. After years of finding scorching giants and molten rock, Kepler-22b felt like a destination. It was proof the mission's core goal was possible. It told us that temperate orbits around sun-like stars weren't empty. They held planets, and if Kepler, looking at one small patch of sky, could find one so fast, then statistically, such worlds had to be common. The question of life shifted. It was no longer if Earth-like orbits existed, but how many millions were out there. This was the milestone, but then, almost immediately, a more sobering reality set in. Kepler-22b's size was a clue. At over twice Earth's width, its density suggested it wasn't a rocky super-Earth. It was almost certainly a mini Neptune. A world with a small, maybe rocky core, but wrapped in a deep, thick atmosphere of hydrogen and helium. A gaseous envelope so immense the pressure at the base would crush any surface. There would be no continents, no shorelines, just an endless, deepening sky that turns into a global ocean of supercritical fluid, a strange state where gas and liquid become one. So while Kepler-22b orbited in the comfort zone, it wasn't a second Earth. Its discovery forced a critical refinement. Being in the habitable zone is necessary, but it's far from sufficient. A planet has to be the right kind of world. It needs a solid surface where chemistry can play out, and an atmosphere thin enough to let light reach the ground, but thick enough to provide warmth and protection. Kepler-22b, for all its symbolic hope, taught us to look deeper. It made the next question unavoidable. If we find a planet the right size, in the right place, what is it actually made of? The hunt now needed a new layer of scrutiny, a way to peer past an orbit and into the essence of a world. The next discovery would do that. It would reveal not just a planet's location, but its astonishing, glittering heart. The idea of a world made of water used to be science fiction. Then we found this planet. GJ1214b. It's about 40 light-years away, a super-Earth, something like 2.7 times the size of our world. But its mass is too low. For a rocky planet that size, the mass should be higher. The math didn't add up for rock and iron. It pointed to something lighter. Something much lighter. The only thing that fit was a composition rich in water, a lot of water. So GJ1214b is likely a water world, a place where continents don't exist. You'd have a global ocean hundreds of miles deep. At the surface, the atmosphere is a thick steam bath, perpetual, but you go down, the pressure builds. It becomes crushing, and under that force the water changes. It doesn't stay a liquid. It transitions into exotic forms of ice, not ice from cold, ice from pressure. A hot, solid crystalline layer, so the ocean has a floor made of ice, a steamy sky, a liquid ocean, and then a solid core of hot ice, a world defined by one volatile element. For the search, this broke the template, the Earth template. Until then, a habitable world meant a mix, land and sea, coastlines. GJ1214b presented a new possibility. A planet that is all ocean, and that forced a question: could a place like that be a home for life? The answer is yes, it could, but the life would be alien. Exclusively aquatic, nothing crawling onto land, no forests. The entire biosphere is in that global sea. The chemistry could be different. On Earth, key reactions happen at interfaces. Where water meets rock, minerals catalyze things. On a pure water world, that mineral boundary is gone. It's buried under hundreds of miles of ocean and that hot ice layer. So life might need other pathways, maybe around hydrothermal vents in the deep dark, independent of sunlight, or maybe in the sunlit upper layers, a floating, planet-wide planktonic civilization. The water cycle would be planetary, a constant churn under that steamy sky. GJ1214b reshaped the criteria. It proved a habitable zone planet doesn't need to look like Earth. It just needs stable, liquid water, and that water can be the planet itself. It steered us toward a new class, volatile, rich super-Earths. These aren't failed gas giants. They formed farther out where ice was plentiful and migrated inward into the temperate zone, worlds of global oceans, or maybe global glaciers over liquid seas. It expanded the palette. From that moment, the search wasn't just for pale blue dots. It was for deep blue marbles, worlds shrouded in steam, holding oceans beneath. And that opened a door to a stranger thought. What if a planet wasn't just rich in water, but in something more exotic, something that glittered? 55 Cancri E. A super-Earth about twice our size. It orbits so close to its star, a year there is just 18 hours. The surface is a lava ocean, 2,000 degrees. But the density was off. For a rocky planet that big, it was too light. The math suggested something else, a composition rich in carbon. The astronomers thought this could be a diamond planet. Under that immense pressure, the carbon in its interior could crystallize. A significant part of it might be one giant diamond, a world of glittering carbon, not rock. For habitability, that's a different lesson. It's not about a place for life. It's about the raw ingredients. 55 Cancri E showed planets can form from very different stuff. Our solar system is oxygen-rich. Rock comes from silicon and oxygen. Carbon is secondary, but around a carbon-rich star, the chemistry flips. Carbon becomes the primary building block. You get worlds of graphite, carbides, and under pressure, diamond. The surface isn't silicate rock. It's something else entirely, and that changes everything for life. Life as we know it is carbon-based, but it needs other things: nitrogen, phosphorus, sulfur, and crucially, water. On a carbon planet, water might be extremely rare. The chemistry for life would need a different solvent, maybe liquid methane or ethane, or it might not work at all. The diamond planet taught us a star's chemical makeup dictates its planets. To find an Earth-like world, we might first need a Sun-like star, one with a similar balance of elements. It added a new filter, stellar composition. Not all stars are created equal, and neither, it seems, are all worlds. But what if you found a world with all the right ingredients, in the right place, around the right star? The next discovery did that. It was the moment the search became real. That diamond world was just one. Then we found a whole solar system. In 2016, astronomers used a small telescope in Chile called TRAPPIST. They saw something around a faint star 40 light-years out, not one planet, 7, Earth-sized. The star is TRAPPIST-1, an ultra-cool red dwarf. It's so dim, you could hold it closer than Mercury is to our Sun and feel nothing. But because it's that faint, the habitable zone is very close, and in that tight space, all 7 of those planets orbit. 3 of them are right in that temperate band, where liquid water could be. This wasn't just one candidate, it was a compact family, a miniature solar system. The planets are so close from the surface of one, you'd see the others in the sky. Not as points of light, but as distinct orbs, some larger than our moon. That discovery reshaped the search. It proved multi-planet, temperate systems are real. They exist around the smallest, most common stars, but a compact arrangement has new rules. The gravitational dance is intense. These worlds tug on each other constantly. That interaction is tidal heating. As the planets flex under gravity, friction makes heat inside them. That could power volcanic activity, or maintain a subsurface ocean under ice, even on a world with little starlight. It introduced a new energy source for habitability, not from the star, but from the planetary family itself. Then, a more revolutionary idea. In a tight system, the environments aren't isolated. If one world has an atmosphere, asteroid impacts could blast material into space. That material, rocks, maybe even hardy microbes, could travel the short distance to a neighbor. The concept of panspermia, life seeding from one planet to another, moves from a fringe idea to a plausible scenario. In a system like TRAPPIST-1, likely. Suddenly, a habitable environment expanded, no longer just the surface of a single, lonely planet. It could be an entire interactive system. Life might not start from scratch on each world. It could hitch a ride. A failure on one world could become a success on the next. That transformed our criteria. We began to look not just for individual planets, but for planetary architectures. A system with multiple worlds in the temperate zone might offer life a better chance, a cosmic neighborhood where resources and maybe life itself could be shared. The search was no longer about a single point of light. It was about finding an entire community. And if life could thrive in a communal setting, what about a world that was utterly alone? The next discovery showed us the ultimate loner, a planet with no sun drifting in the eternal dark between the stars. Proxima Centauri b is next door. 4.2 light-years away, it's a rocky world and it orbits in the habitable zone of the closest star to our Sun. We found it in 2016. That made the search for life concrete. It was a destination, a place we could, in theory, reach within a human lifetime with the right technology. The distance to the stars just collapsed, but this neighbor, it lives under a dangerous sky. Proxima Centauri is a red dwarf, a flare star. It doesn't shine steady. It erupts every few days. Violent outbursts happen. X-rays, ultraviolet radiation, hundreds of times more powerful than our Sun, that blasts its planets. For a world like Proxima b, so close its year is just 11 days, that's an existential threat. A single powerful flare could strip away an atmosphere over centuries. It could scour a surface clean of any complex chemistry, so this discovery forced a revision. A planet can check every box, rocky, Earth-sized, right in the temperate zone. But if its sun is a temperamental monster, all of that can be for nothing. the star's behavior becomes the gatekeeper. Habitability isn't just a property of the planet anymore. It's a relationship, a fragile negotiation between a world and its star. The criteria had to change. We had to include stellar magnetism, flare frequency. We had to learn to read the moods of alien suns, to understand that a quiet, stable star like our own might be a rare gift in a galaxy filled with stellar tantrums. That shifted the whole paradigm. We weren't just planet hunters anymore. We were cosmic matchmakers, assessing the long-term compatibility between a world and its fiery parent. And if a star's fury could render a perfect orbit sterile, what about a star that was just fading away? The next discovery would show us that. A world orbiting a dying sun. A place where time itself was running out. Proxima B had to deal with a flare star, but some red dwarfs are quiet. LHS 1140b orbits one of the calm ones. It's 49 light-years away, and it sits right in the habitable zone. This planet isn't Earth-sized. It's a super-Earth, nearly 1.7 times the size of Earth. But the real story is its mass. It's over 6 times Earth's mass. That means an extraordinary density. It's incredibly heavy for its volume, so it's not a puffy mini Neptune. It's not a global ocean. It's a dense ball of rock and metal. Astronomers think it has an enormous iron core, much larger than Earth's, and that fact changed the checklist for a living world. A massive iron core isn't just geology. It's the engine for a magnetic field. On Earth, our molten outer core churns around a solid iron inner core that generates a dynamo. It creates the shield that deflects the solar wind. It protects our atmosphere from being stripped away. LHS 1140b, with all that hot metal, could power a magnetic shield for billions of years. Even around a red dwarf with its constant particle stream, this world could hold onto its atmosphere, so a planet's interior became a primary criterion. A strong magnetic field went from a hopeful bonus to a likely necessity, but that immense density has consequences. The surface gravity would be about 3 times Earth. Imagine that weight. Walking would be a deliberate, strenuous effort. Mountains couldn't rise as high. The intense gravity would pull them down. You'd get lower, more rounded topography. And it raises a profound question about plate tectonics. On Earth, the slow drift of plates recycles carbon between the crust and the mantle. That geological thermostat regulates our climate over eons. It might even be crucial for a stable biosphere. Under 3 times the gravity, could that process even work? Would the plates lock up, frozen under the pressure? Or would the internal heat, maybe from that giant core, drive a more violent form of geology? We don't know. LHS 1140b taught us a habitable planet is a balanced system. Its sky depends on its heart. Its surface is a product of the forces between them. A world can be in the perfect spot. It can have a protective shield. And it could still be a geologically stagnant desert or a crushing high-gravity prison. So the checklist got more nuanced. It started asking not just if a world could hold an atmosphere, but what kind of world lay beneath it. Kepler-452b is like looking at Earth but through time. It was found in 2015. It circles a star very much like our Sun. And it's in that star's habitable zone, but it's not an exact copy. The planet is bigger, about 60% larger than Earth, a super-Earth, and it's old. Its star system is older than ours by maybe 1.5 billion years. That age, that difference, it changes everything. It asks a question: what if Earth had that much more history? Where would we be now? Kepler-452b is that question. It's Earth's older, larger relative, and finding it made astronomers think about a new factor: time. A habitable zone isn't a fixed location. It's more like a window. A planet can be in it, and then it can leave. For a world like this, age is 2 things. On one side, more time is more opportunity. An extra 1.5 billion years is an almost impossible length of time. Time for life to start, to change, to become complex. If life began there when it did here, it's had 50% more of all Earth's history to develop. The scale of that is hard to grasp, but time changes the star too. Stars like the Sun, they don't stay the same. They get brighter slowly over billions of years. It's a gradual process, inevitable. For a planet at a set distance, that means the heat keeps rising. If there are oceans that can start something, a runaway effect, it gets warmer, more water evaporates. Water vapor traps heat, which makes it warmer, which evaporates more water. It's a cycle. There's no easy way to stop it. In the end, the oceans could boil off completely. The atmosphere turns into a hot, thick blanket. It becomes like Venus. So Kepler-186f is in a delicate position. It's probably getting about 10% more light from its star than Earth gets today. Is it still a world with water, with mild temperatures? Or has that slow brightening already pushed it too far? Is it becoming a Venus, its oceans turning to steam? We don't know, but asking the question changed how we search. We can't just look at where a planet is now and say it's habitable. We have to think about its whole history. We have to ask, how long has it been in that zone? And how much time does it have left? A planet might be in the perfect spot today, but if it just got there, life might not have had time to begin. And a world like Kepler-186f, it might have had billions of years of perfect conditions. A long, stable period for life before the slow heating began. This showed us that a living world isn't just a place, it's an event. A moment where geology and atmosphere and a star's life all line up for a long time, but not forever. So now when we look at other planets, we're not just looking for a picture, we're trying to read its story, to understand its past climate and guess its future. The search became a search for worlds at the right time. Not too early, not too late, but right for now. And if a star like the Sun can end a world just by aging, what happens when the star isn't just aging, but is already dead? The next find would show us that a planet not in a habitable zone, but in a graveyard, orbiting the remains of a sun. A stable orbit gives you time, but that time can end. WASP-12b is a planet that's dying. It's a hot Jupiter, a gas giant orbiting so close to its star that its year is just over one Earth day. The star's gravity is immense. It doesn't just heat the planet, it stretches it, pulls it into a teardrop shape, and the atmosphere isn't just hot, it's being stripped away. A river of gas, thousands of tons every second, flows from the planet toward the star. It forms this thin, hot disk of lost material. We're seeing a kind of cosmic consumption, but the real lesson is in the timing. Precise measurements show the planet's orbit isn't just closed. It's decaying, it's spiraling inward slowly, inexorably. In maybe 3 million years, which is nothing in cosmic time, it will cross a threshold. It will be torn apart. This is orbital decay happening now, a solar system rearranging itself. For the search for life, this is a profound warning. It makes one criterion absolute: orbital stability over geological timescales. Life as we know it needs time, not thousands of years, not millions, billions. It needs eons of stable, predictable conditions. Time for chemistry to become biology, for simple cells to become complex. A planet that's migrating or falling into its star can't provide that. Its environment is temporary. A brief flare of possibility before an inevitable end. WASP-12b is the extreme case, but the principle holds everywhere. A planet might be in the habitable zone today. But if its orbit is chaotic, perturbed by the gravity of other giant worlds, its stay in that comfort zone could be short. It could be flung into the cold outer darkness, or sent careening into the star. Long-term survival is the first filter, the non-negotiable one. Before water, before an atmosphere, before a magnetic field, a world needs a stable address. For ages, this discovery shows us that planetary systems aren't frozen sculptures. They're dynamic, often violent arrangements. Gravity is a constant sculptor. Orbits can change. The peaceful order of our own solar system, where planets have circled for billions of years without catastrophe, might be a special fortune. A quiet neighborhood in a galaxy that often has gravitational upheaval. So when we find a promising world now, we have to ask a new question. How long has it been there? And how long will it stay? The ultimate test for habitability isn't just about where a planet is. It's about the endurance of its journey. 55 Cancri E is a super-Earth. Twice the size of our planet, it orbits so close to its star that a year is just 18 hours. The surface is an ocean of lava, but the density measurements told a different story. For a rocky planet of that size, it was too light. The math didn't point to the silicate rock we know. It pointed to carbon, huge amounts of it. Under the pressure inside that world, the carbon could crystallize. Scientists think maybe a third of the planet's mass is diamond, a whole world built on precious stone. This is more than exotic geology. It's a lesson in chemistry. Our solar system is rich in oxygen. Silicon and oxygen bond to make the rock beneath us. Carbon is secondary here, but around a star with a different recipe, everything changes. 55 Cancri E probably formed from a disk full of carbon. In that environment, carbon becomes the main building block. You get worlds of graphite, worlds of carbides, and under enough pressure, worlds of diamond. The surface isn't stone, it's something alien. For the search for life, this rewrote a basic assumption. It showed that a planet's ingredients, its elemental abundance, set the stage for everything else, the geology, the atmosphere, the potential for chemistry to begin. A carbon-dominated world would have a completely different geology. Silicate rock can flow, allowing for plate tectonics that recycles Earth's crust and regulates our climate. Diamond and graphite are rigid. A diamond planet might be geologically dead. A single, unyielding shell with no renewal. Its atmosphere would come from volcanic outgassing of carbon compounds. Not water vapor, it could be a thick haze of hydrocarbons, and it changes the question of solvents. Life on Earth is carbon-based, but it uses water. On a carbon world, water might be very rare. The chemistry for life would need a different liquid, maybe liquid methane, flowing under a cold orange sky. Or it might not work at all. The diamond planet showed us the recipe for a habitable world has many possible ingredient lists, strange ones. It added a new filter to our search. Stellar composition. To find a world like ours, we might first need to find a star like ours. One with that same delicate balance, the balance that gave us carbon for life, but also oxygen for water and for stone. A true Earth twin needs a cosmic kinship, one that starts in the heart of its sun. The planet might not be the world you'd actually live on. The next frontier could be a moon. Back in 2017, data from Kepler showed something unusual around a planet called Kepler-186f. It's a gas giant. It passed in front of its star, and the light dimmed the way you'd expect. But then, hours later, there was a second, smaller dip in the light, and before the main transit, another subtle dimming. That pattern suggested a moon. A Neptune-sized moon orbiting that distant giant. Then in 2022, another candidate appeared. Data pointed to a possible moon around Kepler 1708b. This one seemed smaller, maybe Earth-sized, orbiting a Jupiter-like planet. Neither is confirmed. These signals are whispers, right at the edge of what our instruments can detect. But the possibility changes everything. It introduces the exomoon. A habitable environment isn't tied to a planet anymore. Picture a gas giant drifting in the temperate zone of its star. The planet itself isn't habitable, but circling it could be a rocky moon warmed by two sources, distant starlight, and then the fierce tidal heat coming from its planetary parent. That moon could have an atmosphere, oceans, continents, and from its surface the view would be staggering. The giant planet would fill half the sky, a banded, swirling colossus just hanging there in a kind of perpetual twilight. The day-night cycle would be this complex dance of eclipses and reflected light from the planet. This expands the search exponentially. For every gas giant we find in a habitable zone, there could be not one, but several moons with potential. The galaxy's real estate for life just multiplied, but living on a moon comes with new, strange rules. Stability is the first one. The moon has to orbit within a safe zone around its planet. Too close and tidal forces rip it apart or lock it, so one face is forever turned toward the giant. Too far, and the planet's gravity loses its grip, and the star can steal the moon away. It's a delicate gravitational balance. Then there's protection. A gas giant often has a powerful magnetic field. A moon orbiting inside that magnetosphere gets a shield. A defense against the stellar wind, like Earth has. Its atmosphere could be preserved by its planet's invisible armor. But there's a flip side. The giant planet itself is a source of intense radiation, trapped in its magnetic belts. A moon might need to orbit in a specific, quieter lane to avoid a constant, deadly bath. The light cycles would be unlike anything on Earth. You'd have the primary day from the star. But then long periods of darkness when you're eclipsed by the giant planet, and at night, a soft, eerie glow from the giant's reflected light. Plants might evolve to use multiple light sources. Life would sink to a rhythm governed by two heavenly bodies. The discovery of these exomoon candidates, even unconfirmed, forces us to rewrite the criteria. We have to consider binary systems of worlds now. A moon's habitability depends on its planet, the planet's mass, its magnetic field, its radiation environment. It's a nested puzzle, and if a moon can be a home, then the most common planets we've found, gas giants, aren't just endpoints. They could be anchors, the central suns of their own miniature, life-bearing systems. This doesn't just add new places to look, it changes the scale of the possible. The color is this deep, brilliant azure. From space, it looks like a serene blue marble, almost a twin to Earth. But this planet, HD 189,733b, is a gas giant. It orbits so close to its star that its atmosphere heats to nearly 2,000 degrees, and that blue isn't from oceans. It's from a haze, silicate particles in the upper atmosphere, tiny fragments of glass scattering the blue light from its sun. The weather there is a nightmare. Those silicate particles don't just float, they form clouds, and then, in that heat hot enough to melt rock, they rain. The planet gets these sideways storms. Storms of molten glass, driven by winds that scream across the surface at over 5,000 miles an hour. That's 7 times the speed of sound. It's a world of relentless, violent meteorology. For the search for life, this hellish place became a classroom. It was the moment we moved from just detecting exoplanets to characterizing their climates. By studying how starlight filtered through its atmosphere and how its heat changed while it orbited, we could map its weather. We learned it has a permanent, scorching hot day side and a slightly cooler night side. And those insane winds are the planet's attempt to balance that, to move heat from the day side to the night. It's a natural thermostat, but a catastrophic one. This discovery reshaped the criteria. It taught us a planet's atmosphere isn't a static blanket. It's an engine, a violent, churning system of chemistry and physics. For a world to be habitable, that atmospheric engine has to run in a gentle, stable mode, not with glass hurricanes, but with soft rains, temperate breezes. The climate of HD 189,733b shows the extreme end. A world where the atmospheric dynamics are so intense they dominate everything. To find an Earth-like world, we now know we must look for the signs of a mild atmospheric engine. One that redistributes heat efficiently enough to prevent deadly extremes, but gently enough to allow for calm seas, quiet skies. We need to understand cloud formation, not of molten silicate, but of water vapor. We need to trace chemical cycles, not of vaporized metals, but of carbon and oxygen. This blue hellstorm, in all its fury, gave us the first detailed model of an alien climate system. It gave us the tools, and the questions will now apply to smaller, rockier worlds. It showed that the difference between a living world and a dead one might come down to the temper of its winds, the chemistry of its clouds. Kepler-186f was discovered in 2020, but the data was old from the Kepler telescope, which had already finished its mission. Scientists were going back through the archive using new algorithms. They found a signal that earlier software had called noise. It was a planet, Earth-sized, orbiting a small, cool red dwarf. And it was sitting right in the middle of that star's habitable zone. The numbers were striking. It gets about 75% of the light Earth gets from our Sun. With an Earth-like atmosphere, its surface temperature could be similar. The headlines called it the most Earth-like planet ever found for size and temperature. A mirror Earth seen in the data. This discovery changed the search. It wasn't about a new telescope. It was about looking again. It showed that our existing archive from Kepler and other missions is still full of undiscovered worlds. The most promising candidates might be in data we've already collected, waiting for smarter tools to find them. The role of artificial intelligence of data mining became central. The hunt is no longer just about bigger mirrors. It's also about better code, algorithms that can spot the faint signature of a small, rocky world. Kepler-186f also showed a strategic shift. It orbits one of the smallest, dimmest stars. For astronomers, that's a gift, because the star is so faint, the habitable zone is very close. A planet there orbits quickly, passing in front of its star often. Each transit is a deeper, clearer signal, compared to a planet transiting a bright, sun-like star. When that planet has an atmosphere, starlight filters through it more noticeably. This makes red dwarf systems, despite their flares, our best current laboratories. They are the places where, in the coming years, we have the best chance to analyze the atmosphere of an Earth-sized world in the habitable zone. To look for signs of life, but maybe the most important thing this mirror Earth brought was a new metric, insolation flux, a precise measurement of the stellar energy a planet actually receives. Not just a vague in-the-zone check. Kepler-186f gets 75% of our sunlight. That exact number lets us model its climate with more accuracy. We can ask, with an Earth-like mix of gases, what would its global temperature be? Would it be a world of glaciers or temperate oceans? This moves us from a binary question, is it in the zone, to a scale of possibility. A world getting 90% of our sunlight might be a lush greenhouse. One getting 110% might be near a runaway effect. Insolation flux gives us the numbers to build those models. It turns habitability from a region on a diagram into a calculable energy budget, and it asks us to consider a biosphere under an orange sky with 3/4 of our light. Could forests evolve there? Would photosynthesis use different pigments? This rediscovered world from the archives didn't just add another candidate. It sharpened our tools. It told us to look back, to look closer, to measure with a finer touch. And if we can find a near twin by re-examining old data, what astonishing oddities might we have missed? The next discovery would be a world that defied every expectation of where a planet could even form. Finding a mirror Earth in the data was one thing. But then we found a world we could actually point to for the future. In 2020, NASA test mission found it, TOI 700D, the first Earth-sized planet in a habitable zone that TESS ever discovered. This wasn't a rediscovery, it was a fresh target announced in real time, and it was perfect. The planet orbits TOI 700, a quiet, small M-dwarf star. 100 light-years away, it's one of 3 planets there, but it's the outermost one, sitting right in that temperate band where liquid water could exist. Its year is just 37 days, but the star is calm, inactive. It doesn't bombard its planets with deadly flares. That makes TOI 700d something special. A prime candidate, it's now a top priority for the James Webb Space Telescope. This discovery marks a shift, a fundamental one. The Kepler mission gave us a census. It told us statistically how common planets like Earth might be. TESS is about the next step, TOI 700d specifically. It's about moving from statistics to investigation. From counting worlds to studying one in profound depth, the criteria for habitability are about to be tested in a laboratory 46 trillion miles away. With Webb, astronomers will try to capture the starlight filtering through its atmosphere. If it has one, they'll look for the chemical fingerprints. Water vapor, carbon dioxide, methane. They'll search for that telltale imbalance of gases, the kind that, on our world, is maintained by life. TOI 700d reshapes the search. It provides a real-world testbed. For years, our criteria have been a list, theoretical requirements, the right size, the right orbit, the right star. A magnetic field, plate tectonics. Now we have a world that checks many of those boxes, and we have the tool to go and look. We're about to move from asking, could this world be habitable, to asking, is it? We're turning the corner from mapping the territory to landing on the shore. This transition changes the quest. It turns abstract probabilities into concrete, observable science. The discovery of this one quiet world around its one quiet star gives us a singular focus, a place to point our most powerful eye and seek an answer to the oldest question. Are we alone? The criteria are no longer just a filter, they're becoming a checklist, one we can finally, truly begin to mark off for a real, distant world. And if we can begin that work on an Earth-sized planet, what about a world that is nothing like Earth at all? A place where the very ground beneath your feet is a memory, and the sky is an eternal, starless black. The search had its first real test, but before we could even aim the best telescope, something else happened. In 2019, astronomers said they found water vapor in the atmosphere of a planet called K218b. This wasn't a gas giant, it was a super-Earth. More than twice Earth's size, in the habitable zone of a quiet red dwarf. For the first time, we had a key ingredient for life, found in the sky of a world that could be temperate. The data was from Hubble. It came from stitching together multiple transits. Starlight passed through the planet's thin atmospheric shell, and the signature of water molecules was there. Clear in the spectrum, that was the breakthrough. It moved the search from geometry and orbit to chemistry. We weren't just finding dots of light anymore. We were tasting the air of another world. But K218b isn't a second Earth. The same data suggested its atmosphere is rich in hydrogen, thick with it, which paints a different picture. The planet is likely what's now called a Hycean world, a new category. Imagine a planet with a rocky core, but over that, a global ocean. Not hundreds of miles deep like earlier ideas of water worlds, a planet-wide sea, and over that ocean an atmosphere, not of nitrogen and oxygen, but of hydrogen. A deep, thick, warm hydrogen envelope. From space, it might look smooth, a featureless pale blue or pinkish marble. The surface pressure under that sky would be immense. But at the interface between that deep ocean and the thick atmosphere, conditions could be stable. In theory, liquid water could exist. The hydrogen atmosphere acts like a powerful greenhouse blanket. It traps heat from the dim red sun. It could keep the ocean liquid even on a world that gets less stellar energy than Earth. This reshaped the criteria in 2 ways. First, it made atmospheric spectroscopy the central tool, the ultimate instrument. Finding a planet in the zone is step 1. Step 2 is reading its light. Looking for biosignatures, not just water but oxygen, methane, combinations of gases that shouldn't exist together without something alive to replenish them. K2-18b proved we could take that step for smallish worlds in the zone. It validated the method. Second, it introduced the Hycean world as a legitimate, broad habitat. This concept exploded the narrow Earth-centric model. A habitable environment no longer needs an Earth-like atmosphere. It could be a global ocean under a hydrogen sky. Life there would be utterly alien, existing in a dark, high-pressure aquatic world, never seeing the stars, drawing energy from chemical vents or from the faint glow filtering down through that immense atmospheric blanket. The potential for such worlds is vast. They could be incredibly common, more common than Earth twins. The galaxy might be filled with these warm, water-rich marbles shrouded in hydrogen. And if life can emerge in a Hycean ocean, then the cosmic address for biology just got much larger. The discovery forced a question: are we looking for the right signs? On a Hycean world, the biosignatures might be different. Not oxygen, but maybe dimethyl sulfide or other molecules. We have to learn a new chemical language for life. The criteria isn't a fixed list anymore. It's a growing, adapting field guide to alien possibilities. And if a world can be habitable under a crushing hydrogen sky, what about a world with no sky at all? A planet sealed under a shell of ice, hiding its ocean from the universe. The chemical signs of a Hycean world are whispers in starlight. To hear them, we needed a new way of seeing. For a long time, most exoplanets were ghosts, just wobbles or shadows, but in 2020 that changed. We saw one, not as a dip on a graph, but as its own point of light, separate from the star. That world was Beta Pictoris c, a gas giant orbiting a young, bright star 63 light-years away. This was direct imaging, the goal of planet hunting. Pulling that faint speck from the star's glare is like spotting a firefly next to a lighthouse from thousands of miles away. But the real change wasn't just the picture. It was the story behind it. Astronomers already knew this planet was there. They'd found it years before, not by seeing it but by feeling it. They used the radial velocity method, measuring the subtle tug of the planet's gravity on its star. That gave them its mass and its orbit. They knew exactly where and when to look. Then, with a powerful gravity instrument on the Very Large Telescope, they pointed and captured it. For the first time, we had a planet whose mass we knew from one technique and whose light we captured with another. This fusion of methods is the future. It's the shift from discovery to deep characterization. For a gas giant like Beta Pictoris c, this synthesis tells us about its formation, its atmosphere, its place in a young system still full of dust and comets. But for the hunt for Earth-like worlds, this approach is everything. Imagine finding a small, rocky planet in the habitable zone using the transit method. You'd know its size, but to know if it's truly Earth-like, you need its mass. From mass and size, you get density, rock or gas, a global ocean or a continent. Radial velocity can give you that mass. Then, with a next-generation telescope, you might directly image it, isolate its faint glow, and from that light you can take a spectrum. You can read the chemical makeup of its atmosphere without the overwhelming light of its star polluting the signal. You can search for water, oxygen, methane. The biosignatures, Beta Pictoris c, proved this forensic synthesis is possible. It showed that confirming a habitable world won't come from a single, triumphant image. It will come from a patient, multi-year campaign, a convergence of evidence from different instruments, different techniques, all pointing to the same conclusion. This is the new standard. It moves us from simply finding planets to truly knowing them, to building a complete dossier on a distant world. its orbit, its mass, its climate, the chemistry of its sky. The next generation of telescopes, like the Habitable Worlds Observatory now being planned, is designed for this exact purpose, to perform this synthesis on Earth-sized planets around Sun-like stars. The discovery of Beta Pictoris c wasn't about the planet itself, a scorching young giant. It was about the blueprint it provided, a roadmap for how we will one day introduce ourselves to a living world. And if we can build such a detailed portrait of a distant giant, what happens when we turn that same forensic eye on a planet that is, by all accounts, a perfect mirror of our own? Density tells you what a planet is made of. A high number, that's rock and iron packed in tight. A low number means gas, light and puffy. But then we found planets where the story didn't fit. The Kepler-186f system, a young star with 3 worlds orbiting it. Each one is several times the mass of Earth, so you'd expect them to be dense. But they're not. Their densities are some of the lowest we've ever seen, lower than cotton candy. Astronomers call them super puffs, and they're not gas giants, not like Jupiter. They're something else. They have the mass of a substantial world, but their volume is enormous. They're bloated, swollen, with an atmosphere so extended, so fluffy, it doesn't match any model of how planets form. How they evolve: picture a small, dense core, maybe rocky, maybe icy, but wrapped around that core is an atmosphere, hydrogen and helium, hundreds of miles thick. Maybe thousands, an atmosphere so vast, so thin, that at its outer edges it has almost no weight. A planet that is mostly sky. For habitability, that's a lesson in extremes. Atmospheric retention is fragile. It's a complex art. How does a world hold onto an envelope that gossamer? The gravity at the top of that atmosphere is incredibly weak. A gentle stellar breeze should blow it all away in a cosmic instant, and yet there it is. So we have to rethink the mechanisms. What preserves an atmosphere? Maybe a strong magnetic field holds it in place, like an invisible bottle. Or maybe the planet is just very young. It hasn't had time to lose its primordial hydrogen shroud. Or maybe it's being replenished by comets or outgassing from within. Studying these cotton candy worlds teaches us about a planet's sky, its entire life cycle. It shows us the full spectrum, from the crushing, deep atmospheres of mini-Neptunes to these delicate, extended super puffs, and somewhere in the middle of that spectrum is a world like ours. A rocky body with a modest, life-giving blanket of air. Our atmosphere isn't the default, it's a specific outcome, a delicate one, a balance between what was captured at birth, what was vented from the interior, and what was retained. Against the relentless push of the stellar wind, the super puffs show that atmospheric mass and composition are independent. A planet with Earth's mass doesn't have to have Earth's atmosphere. It could have one 100 times thicker or one 1,000 times more tenuous. It could be a crushing greenhouse or a wispy, cold enigma. This discovery reminds us, our own blue marble with its thin shell of breathable air is just one point on a vast continuum of possibilities. And if a planet can be mostly sky, then what about a world that is mostly core? A place where the atmosphere was never there or was stripped away to reveal a bare metallic heart. Our solar system has a lot of space, big gaps between the planets, but that might be unusual. Back in 2010, astronomers were looking at a star, HD 10180. A Sun-like star, and they found something more common, a packed system. They saw evidence for maybe 7 planets, all of them orbiting closer to their star than Mars is to our Sun. It's a tight, busy place, a miniature solar system with no extra room. Those planets, most of them Neptune-sized or bigger, they have orbits that take days or weeks. Not years. Their gravity is always pulling on each other. A constant, quiet back and forth. We used to think our orderly setup was the standard. Systems like HD 10180 showed it isn't. These compact systems are probably the norm. especially around stars with more heavy elements, and that changes the basic picture for a habitable world. A planet isn't alone, its family matters. In a crowded system, gravitational nudges are just part of life. Those nudges can do two things: they can break things down. Over time, all those little tugs can push a planet into a wild orbit, or even kick it out of the system completely. That's one path, but they can also regulate. Think about Earth's own climate history. Our ice ages, the warm periods, they're partly set by slow, cyclical changes in our orbit and our tilt, the Milankovitch cycles. Driven by the gentle pull from Jupiter and the other planets, in a tight system like HD 10180, those nudges would be stronger, more frequent. They could create much bigger, faster climate swings on any world in the right zone. So for habitability, it adds another condition: long-term climate stability. A planet could have liquid water right now, but if its orbit is constantly being adjusted by big neighbors, its climate might swing violently over thousands of years. Glaciers could come and go on a scale that makes our ice ages seem quiet. Could life adapt to that kind of rhythmic, global change? Maybe, but complex life, multicellular life, might need longer stretches of calm to really get started. Systems like that one teach us something. A planet's true habitability comes from its whole celestial community. A stable, life-friendly orbit isn't just about the right distance from the star. It's about the gravitational harmony or the discord of every other world in the family. A planet's siblings can be the source of its stability, gently pacing its climate. Or they can be what destroys it, pulling it into chaos. So now, when we find a promising world, we have to look at its neighborhood too. We have to ask, who are its neighbors? And are they keeping the peace, or are they stirring up trouble? Teegarden's star. It's a red dwarf, very faint, very old, only about 12 light-years away. But it was so dim we didn't even find it until 2003. Then in 2019, we found two planets there, Teegarden's B and Teegarden's C, both rocky, both in that star's habitable zone. And when they were scored on the Earth Similarity Index, they came out very high. For planets around small stars, some of the highest scores we've seen. That index, it's a calculation. It takes a planet's size, its density, the energy it gets from its star, its surface temperature with an Earth-like atmosphere. And it compares all that to Earth. A perfect match would be a 1, 0. Teegarden's B scored a 0, 0.5. Planet C scored 0, 0.4. On paper, they're among the closest mirrors to Earth we've found. And they orbit the most common type of star in the galaxy, so this refines things. It moves from general hope to specific comparison. We can line these worlds up next to Earth. Their size is right, their estimated temperature is right, their star is small but it's quiet, billions of years stable. That systematic scoring makes them the frontline test cases. If life is common, these are the kinds of worlds where we'd have our best chance, right in our backyard, but that high score also shows what we don't know. The index measures similarity, not habitability, and there's a major question. Both planets are almost certainly tidally locked. One side always faces the star, perpetual day. The other side is endless night. For a long time, we thought that was a death sentence. The day side overheats, the night side freezes. Any atmosphere would condense on the cold side. The planet would be barren, but newer climate models suggest a possibility. If these worlds have atmospheres, even a fraction as thick as Earth's, global winds could circulate the heat. They could move warmth from the day side to the night side. That might prevent total collapse. The result could be a temperate band along the twilight line. Or even a globally mild climate. That word, if they have atmospheres, that's the central debate now, and Teegarden's worlds are at the heart of it. Their quiet, ancient star is a plus. It hasn't blasted them with flares that could strip an atmosphere away early on. but have they held onto one or made a new one? Do they have magnetic fields to protect it? We can't tell from here, so their discovery sharpens the criteria. It tells us the next leap won't come from finding more planets that score well on an index. It will come from answering the atmospheric question for planets just like these. They're the current pinnacle of the search around red dwarfs, the best possible cases based on everything we can measure from a distance. And in doing that, they frame the next step, to look not at their orbits but to taste their skies, to search for the chemical fingerprint of an atmosphere on a world locked in an eternal embrace with its dim sun. That answer will define the future of the search. A planet with 2 suns used to be just science fiction. Then we found Kepler-186b, Saturn-sized world orbiting 2 stars. A binary system. From the surface you'd see 2 suns, one larger, orange, the other smaller, red. They orbit each other every 41 days and the planet goes around them both. That proved something basic. Planets can form and survive inside the complex gravity of a multi-star system. And if a gas giant can be there, maybe a rocky moon around it could too. Or a terrestrial planet farther out in a safer orbit. That discovery, it expanded the map. Potential homes could include binary systems, even trinary ones. The galaxy is full of them. More than half of all stars have at least one companion. So the real estate for life, it just grew. A lot, but living under 2 suns that has its own rules. Habitability criteria now has to consider a dynamic environment. The light isn't constant. There are complex patterns, light and dark, an eclipse, one star blocking the other. Periods of double daylight, then times of single sunlight or even none as the planet moves and the stars align. The radiation changes too. Different stars emit different light, different stellar wind. A world there is bathed in a shifting mix. Its atmosphere would have to be resilient, and then there's gravity. The pull from 2 stars creates zones of stability and zones of chaos. For a planet to have a stable, circular orbit in the habitable zone, it has to be carefully placed, too close to the pair, and the gravitational tug of war would tear it apart or fling it away. But Kepler-186b showed these stable niches do exist, places where a world can last for billions of years. Imagine a rocky moon orbiting a gas giant in a system like that. Its climate would be complex. The day-night cycle comes from the moon's rotation, but the length and intensity of daylight is shaped by the stars' dance. Seasons wouldn't just come from a tilt, they'd come from the changing distance, the combined light of 2 suns. Life there would adapt to a different rhythm. Plants might have sensors for 2 light spectra. Animals might sync their activities to the predictable pattern of eclipses. The whole idea of a stable climate, it expands. It's not about constancy anymore. It's about predictable, cyclical variation. A world can be habitable even if its energy source is a duet, not a solo. This discovery, this Tatooine planet, it taught us to look for life in the most storied settings of our imagination. It proved the galaxy's most common stellar arrangements aren't wastelands. They're new stages with new rules, and if a world can find stability with 2 suns, what about a world with no sun at all? A planet alone, drifting in the cold between the stars. GJ367b is a planet made of metal. It's only about 70% the size of Earth, so it's roughly the size of Mars, but its mass is huge. For its volume, it's one of the densest planets we know. The numbers are clear. This isn't a rock, it's a ball of iron, an iron planet, and it orbits in a furnace. It circles its red dwarf star in just 8 hours. A year there is 1/3 of an Earth day. The surface temperature is probably over 2,000 degrees, a permanent molten twilight. This world changes the criteria by showing an endpoint. A final state. Astronomers think GJ367b is almost certainly a planetary core, the exposed heart of what was once a bigger world. Imagine a planet, maybe a super-Earth with a rocky mantle and a thick atmosphere. It formed too close to its star, or it moved inward, and in that inferno the star did its work. The intense radiation and stellar winds over eons stripped away everything that wasn't held by strong gravity. The light gases went first, then the silicate rock, the mantle, was boiled and blasted away. All that's left is the heaviest part, the dense iron-nickel core. It's a skeleton, a cosmic relic of a world that was completely taken apart. For habitability, this is a lesson in cosmic violence. It shows the opposite end from water worlds and Hycean planets. Those are volatile rich. GJ367b is volatile poor. It's been scoured clean. It represents a pathway of total loss, a reminder that a planet's location isn't just about temperature. It's about survival. To become an Earth, a world has to avoid this fate. It has to form at a safe distance or migrate there gently. It needs a magnetic shield to protect its atmosphere from erosion. It has to hold onto its water and its gases against the constant push of its star. Understanding this iron world helps us model planetary destruction. By studying its orbit and composition, we learn about the processes that can strip a world bare, and that helps us appreciate the specific, delicate history of our own planet. Earth kept its volatile elements, its water, its nitrogen, its carbon because it formed in a quieter neighborhood. Its core stayed buried under a protective mantle and crust. Its magnetic field held back the solar wind. GJ367b is a stark contrast, a monument to a different history, one of catastrophic loss. It expands the catalogue of what's possible to almost surreal extremes. We have planets of diamond, planets of water, and now a confirmed planet of iron. A gleaming, heavy marble orbiting in a perpetual blaze. It tells us the outcomes of planetary formation are more diverse and often more brutal than we imagined. And it makes our own blue world, with its thin shell of air and its vast oceans, seem not just fortunate but miraculously preserved. A gentle outcome in a universe full of violent endings. Statistical surveys of exoplanets showed this strange gap, an empty patch. Astronomers call it the Neptune Desert. It's this region close to stars where orbits are just days long. And in that zone, you almost never find planets the size of Neptune. It's a place of scarcity. Where you'd expect to find many worlds, you find almost none. That empty spot tells a story. It's about what happens to a certain kind of planet when it gets too close. The desert exists because of a brutal process. A Neptune-sized world, a sub-Neptune, has a substantial rocky core, but it's wrapped in a thick atmosphere, hydrogen and helium, a volatile, rich world. If that planet moves inward or forms too close, it enters an inferno. The stellar radiation is relentless. It heats that puffy atmosphere to extreme temperatures. It gives the gas molecules enough energy to escape. The atmosphere doesn't just sit there, it evaporates. It boils off into space, stream by stream, over millions of years. What's left behind after that unraveling is often just the dense, rocky core, the skeleton of the former world. We've likely already found the results. Those ultra-dense, iron-rich planets, like GJ367b, they are the survivors, the ones who made it through the storm, stripped bare. For the search for life, this pattern changes things. It reshapes the criteria. It adds a new dimension, time, history. A planet's current state is just a single frame in a long movie. The Neptune Desert tells us that many rocky super-Earths we find in temperate orbits today, they might not have been born rocky. They might be stripped cores, former sub-Neptunes, worlds that started life farther out, as volatile, rich ice giants, and then migrated inward, not all the way into the furnace, but just far enough. Just far enough to lose their thick gaseous envelopes, leaving behind a bare, rocky body. And then, perhaps through further interactions, they settled into a stable orbit. A temperate orbit, a second chance. This means a potentially habitable rocky planet might have a very different biography than Earth. Earth formed rocky from the start. In the temperate zone, it slowly built its atmosphere and oceans from within, from comet deliveries. A desert survivor built its core first, then it donned a giant gaseous cloak. And then had that cloak violently torn away, leaving it exposed. Its surface would be a fresh start. Outgassing from its interior could then build a new atmosphere. A secondary atmosphere made of heavier gases, water vapor, carbon dioxide, nitrogen, the kind of atmosphere that could nurture life. So when we look at a rocky exoplanet in the habitable zone now, we have to ask new questions. What is its migration history? Is it a primordial rocky world or an evaporated core? Each history implies a different starting chemistry, a different inventory of water and organics. A desert survivor might have been thoroughly baked, its surface remelted during the atmospheric loss. It could be bone dry, or its original icy mantle could have melted during the process, delivering a global ocean as the atmosphere blew away. The Neptune Desert, this empty zone on a graph, teaches us that habitability isn't just about where a planet is. It's about the journey it took to get there, the violence it endured, the transformations it survived. To understand a world's potential, we must try to read its past. The criteria now must include planetary archaeology, piecing together the life story of a distant point of light. And if a planet's past can be reshaped so dramatically by its star, what happens when the star itself is not one, but two? Locked in a dance so close they nearly touch, the next discovery would show us a planet orbiting at the very edge of stellar destruction. The search was about history, about survival, but to answer it, we had to stop just finding worlds and start reading their stories. The James Webb Space Telescope let us do that. Its first big results weren't about new planets. They were about taking apart the atmosphere of one we already knew, WASP 39b, a hot Saturn over 700 light-years away. The planet passed in front of its star, and Webb's instruments caught the starlight passing through its puffy atmosphere. The data that came back, it was a revelation. It wasn't just a detection, it was a full chemical list: carbon dioxide, water vapor, carbon monoxide, sodium, potassium. And then something we didn't expect, a clear signature of sulfur dioxide. First time sulfur dioxide had ever been found in an exoplanet atmosphere, and its presence told a story. The star's ultraviolet light was breaking apart water vapor up in the air. That released oxygen and hydrogen atoms, and those reacted with other things to form sulfur dioxide. That's photochemistry, an active chemical engine driven by starlight. For a world like WASP 39b, that's fascinating weather, but for the search for life, it's proof. Webb showed we can move past the simple question, does it have an atmosphere, to the complex one, what's happening inside it? We can decode the chemical cycles, the layers, the interaction between a star's light and a planet's sky. This tool will soon point at cooler, rockier targets, worlds like those in the TRAPPIST-1 system. The idea of habitability is being rewritten right now by this. It's not a list of static conditions anymore. It's becoming a search for chemical narratives. Soon, when we look at a temperate, Earth-sized world, we won't just check for water vapor. We'll look for chemical disequilibrium. On Earth, our atmosphere is in a state that chemistry alone can't maintain. We have lots of oxygen, which is highly reactive, alongside methane. Left alone, they'd combine and vanish. The only reason they coexist is because life is constantly pumping them into the air. Plants make oxygen, microbes make methane. That persistent imbalance is a potential biosignature, a sign something alive is changing its environment. Webb's analysis of WASP 39b gives us the blueprint for finding clues like that. We'll measure not just what gases are there, but their ratios. We'll look for the fingerprints of aerosols and clouds which shape a climate. We'll search for chemicals that shouldn't be there without an explanation. The presence of certain compounds like dimethyl sulfide, which on Earth is made by marine plankton, could be a hint. This turns the search into a chemical detective story. We'll be looking for anomalies, for whispers of process in the data. The old criteria asked if a planet could, in theory, support life. The new standard, made possible by Webb, will ask if a planet's atmosphere shows signs that it already does. It shifts the quest from the geography of orbits to the forensic science of alien air. And if we can read the complex chemistry of a distant sky, what might we learn from a planet with no atmosphere at all? A world laid bare, its history written right on its scorched and silent surface. Webb showed us how to read alien skies, but some planets don't have a sky. They don't orbit a star. They're nomads, drifting in permanent night. We call them rogue planets. Worlds that formed in a solar system, then got thrown out by a gravitational encounter, ejected. They wander alone. For a long time, they were theoretical. Then we started finding them through microlensing. The method goes like this. A rogue planet, invisible in the dark, passes in front of a distant star. Its gravity becomes a lens. It bends the starlight, magnifies it just for a moment, a brief brightening in the data. These events are rare, they're fleeting. But the surveys point to something astonishing. They suggest rogue planets might outnumber stars. There could be billions, trillions even, silently moving through the galaxy. This stretches the idea of a habitable place to the limit, to a place with no sun, no day, no seasons, just starless black, and yet life there isn't impossible. It just needs a different kind of warmth. Imagine a large, rocky rogue planet, one that kept a thick atmosphere of hydrogen. That atmosphere would be a phenomenal greenhouse blanket. It would trap any internal heat the planet generates, stop it from leaking into space, and that internal heat is the key. It comes from the slow decay of radioactive elements in the core. Elements like uranium and thorium. This radiogenic heat is what keeps Earth's core molten. It powers our magnetic field, our volcanoes. On a rogue planet, sealed under a thick hydrogen sky, that same gentle warmth could keep the surface above freezing. Even in the deep cold between stars, or think of a different version, a rogue world with a thin atmosphere or none, its surface would be frozen, but deep under an icy crust, a subsurface ocean could persist. Heated from below by that radioactive decay, insulated from the cosmic cold by miles of ice, a dark, global sea, completely cut off. In both cases, the rules for habitability get rewritten. Starlight isn't a requirement anymore. The energy source turns inward. It becomes geological, planetary. A world's own radioactive heart becomes its sun. Its thick atmosphere becomes its greenhouse. Its icy shell becomes a protective dome. Life in a place like that would be utterly alien, a biosphere with no connection to the galaxy. No concept of a sky. If it exists in a subsurface ocean, it would be a blind ecology, adapted to pressure, thriving around hydrothermal vents in endless dark. Chemosynthesis, not photosynthesis, would be the foundation. The whole web of life built on chemical energy from the planet's interior. This changes where we have to look. The loneliest, coldest places now enter the search. It means a habitable world isn't defined by its orbit. It's defined by its internal fire and its ability to keep that fire banked. A rogue planet is the ultimate test of resilience, a world that carries everything it needs within itself. No parent star, no celestial family, just a solitary traveler holding onto its warmth against the endless cold. And if life can persist in that kind of isolation, then the galaxy isn't just a collection of bright solar systems. It's also a vast, dark ocean filled with silent, wandering worlds. Each one a potential arc carrying the possibility of life through the void, independent of any star's light. Venus is a warning. It's nearly Earth-size, formed in the same part of the solar system from the same stuff. But it turned into a furnace where lead flows like water under a sky that's just a crushing weight of carbon dioxide. For a long time, we thought of it as our opposite. A cautionary tale, but with exoplanets, Venus became a category. Astronomers now talk about the Venus zone. It's the inner frontier, just inside what we used to call the habitable zone, where a planet gets a little too much energy from its star, enough to start a feedback loop with no way back. The idea is simple, but the lesson is deep. A planet in the Venus zone isn't doomed from the beginning. Its fate depends on the atmosphere. If it has too much of certain greenhouse gases, like water vapor or carbon dioxide, a process kicks off. The star heats the planet. That heat evaporates more water, and water vapor is a powerful greenhouse gas, so it traps more heat, which evaporates even more water. The cycle runs away, the oceans boil. All that water vapor in the upper atmosphere gets broken apart by ultraviolet light. The hydrogen escapes to space for good. The oxygen that's left reacts with the rocks. The planet is left bone dry with a thick, choking atmosphere of carbon dioxide, a permanent greenhouse. That's the runaway, and once it starts, it can't be reversed. The planet crosses a line from a potential garden world to a permanent hellscape. We've found exoplanet candidates in that position. Worlds that might be like Venus. GJ 1132b is one. A rocky planet about 1.2 times Earth's mass, but it orbits so close to its dim red dwarf that the surface is probably scorching. Yet studies suggest something remarkable. It might have a secondary atmosphere. Astronomers detected an atmosphere around it, likely rich in hydrogen or hydrogen cyanide. This is a world that may have lost its first, thick atmosphere to the star's fury and is now outgassing a new one from volcanoes. It's a snapshot of atmospheric evolution, or maybe atmospheric death throes. Studying worlds like that is like watching the story of Venus play out somewhere else, and it changes how we look for habitability. The habitable zone isn't a safe harbor. It's more like a narrow channel with a deadly shore on either side. The outer edge is the freeze line where a world becomes a snowball. The inner edge is the Venus zone, the boil line. A truly Earth-like planet has to navigate between them for billions of years. So just finding an Earth-sized planet in the broad habitable zone isn't enough anymore. We have to ask, which side of the climate knife edge is it actually on? Does its atmosphere have the right composition to reflect just enough heat or trap just enough to stay in balance? Understanding the Venus zone puts climate modeling right at the center of the search. We have to simulate whole planetary histories. We take a world size, its star's output, its likely starting water, the chemistry of its volcanic gases. We run the model forward through billions of virtual years. Does the climate stabilize, or does it spiral into a runaway greenhouse or a global ice age? Those simulations tell us which of the promising exoplanets are the best bets. They help us tell a true Earth twin from a Venus in disguise, a world that looks right but whose climate destiny is a toxic trap. So Venus, our failed twin, becomes our most important teacher. Its hellish conditions aren't a mystery. They're a predictable outcome of physics and chemistry. By defining the Venus zone, we learn to read the subtle signs in other solar systems. We learn to recognize the planets standing on the brink. It adds a critical layer. The search isn't just about finding a planet in the right place anymore. It's about finding a planet with the right story, a story of climate stability written in the delicate balance of its sky. And if a planet's atmosphere can tip it into an eternal furnace, what other delicate balances are there? What unseen forces beyond the light of its star might push a world toward life or condemn it to silence? The final discovery would point to a force not from above but from deep within. Proxima Centauri is the star next door. It's a red dwarf just over 4 light-years away. We already knew about one world there, Proxima b, but in 2022, astronomers saw a new signal, a second, much smaller tug on the star. They named the candidate Proxima d. Its estimated mass is astonishingly low, possibly just a quarter of Earth's mass. That would make it lighter than Mars, and its tentative orbit is in the star's habitable zone. This isn't confirmed yet. It's a candidate, a whisper in the data that needs more listening. But if it's real, it changes the game. For years, the search focused on Earth-sized planets. Worlds with enough gravity to hold a substantial atmosphere, enough mass for geological activity, for a magnetic field. Proxima d challenges all that. A mere quarter Earth mass, it suggests the habitable zone might not be reserved for planets of a certain size. It could be home to a much wider family. From super-Earths down to small, Mars-like worlds, this pushes detection to its absolute limit. Finding the gravitational pull of such a tiny world around a restless star is like trying to hear a single soft note in a roaring symphony. The fact that we might be doing it reshapes the criteria. It forces the question, how small can a habitable world be? A planet with such low gravity faces immense challenges. Holding onto an atmosphere against stellar winds would be difficult. Its internal heat from radioactive decay would be less. That could lead to a geologically dead world, frozen solid. But these are not certainties, they are possibilities. A small world could maintain a thick atmosphere if it formed with one and orbits a very quiet star. It could have geological activity driven by intense tidal forces from its sun, a constant internal kneading. It could even host a subsurface ocean, sealed and warmed from within. The presence of liquid water, the baseline for habitability, becomes less about planetary mass, more about a specific, delicate balance: atmosphere, stellar energy, and internal heat. Proxima d, this faintest of hints, expands the palette of life once more. It tells us a living world might not need the heft of Earth. It could be a smaller, more fragile marble. A place with a thinner sky, lower mountains, a more intimate scale of existence. If such diminutive worlds can exist in temperate orbits, then they are likely incredibly common. The galaxy might be filled with these small, potential gardens, worlds we have only just begun to sense. This brings the search full circle, back to our nearest stellar neighbor. The cosmos holds its secrets in all sizes. The final reshaping of the criteria may be this: habitability is not a club for planets that look like ours. It is a spectrum of possibilities, a conversation between a world and its star, conducted across a scale we are only now learning to hear. We've moved past the old checklist. The Goldilocks zone, that idea of a planet just like ours, it's gone. These discoveries, from pulsar graveyards to Hycean ocean worlds, they've dismantled it. They've given us something richer, a whole spectrum of possibilities. A habitable world isn't one destination anymore. It's a range, places where life could cling on, in ways we're only starting to imagine. The criteria have stretched. It's not just about a star's gentle light. It's about a planet's violent history, its migration, its survival. It depends on the chemistry of an alien sky. The whispers of water vapor, the unexpected presence of sulfur dioxide. It can draw heat from a radioactive core, warming a rogue planet in eternal dark. It's shaped by gravitational nudges from neighbors, by the protective embrace of a magnetic field generated by a world's molten heart. Every new layer adds depth to the portrait. A possible home, and as the James Webb Space Telescope and the missions after it peer into these atmospheres, they're not just collecting data, they're translating a new language. Each spectrum, each chemical signature is a sentence, a story we're learning to read, the story of how common the conditions for life might be, or how rare. The search has changed. We're not looking for a second Earth anymore. We're looking for the diversity of life's potential homes across the galaxy, diamond worlds. Iron cores, worlds with 2 suns, worlds with none. The cosmos has shown us the recipe for life isn't one rigid formula. It's a library of recipes, each written in a different dialect of physics and chemistry.